Welcome to today's broadcast. My name is Barbara Lingberg, and I am the sponsor for FAA's Software and Digital Systems Research Program. Today's broadcast is the result of our research effort to address data integrity approaches. Thank you for joining us in this rescheduled event. Thanks also to those who offered to meet in conference rooms so that additional people could join us live today. As mentioned in the invitation, this broadcast is being recorded. You can tell this by the red dot in the green participants bar at the top of your screen. If you do not or you cannot agree to such recording, then please leave the broadcast now. By remaining on, you automatically consent to its recording. All the attendees except the pre-designated panelists are muted. If you have a question for the briefer, please submit it in the Q&A window to all panelists. Mike DeWalt will serve as moderator for questions, reviewing or grouping them as needed. He will read them to the briefer at appropriate times. Today's broadcast will last no more than 2 hours. If all questions cannot be answered within the allotted time, they will be answered later and responses amended to the recording itself. Within a few days, I will send an email to all invitees with the URL for the recording. However, if you want to address the slides prior to that email, Dr. Koopman will identify their web location during his briefing. Thank you again for joining us today. And now Chuck Kilgore, the Software and Digital Systems Research Program Manager, will introduce the briefer and principal investigators for this research effort. Chuck?
Yes, thank you, Barbara. This is Chuck Kilgore, and we manage the research program called Data Integrity Techniques. And I'm going to introduce Dr. Philip Koopman, who is an associate professor at the Carnegie Mellon University Electrical and Computer Engineering Department. His background includes time as a Navy submarine officer, chip designer at Harris Semiconductor, and embedded system researcher at United Technologies Research Center. He currently teaches embedded system courses at Carnegie Mellon. His current research areas include lightweight software processes for embedded systems, deeply embedded system security, autonomous system robustness testing, and embedded system safety. He has been working in the area of CRCs and checksums since 2001. Assisting Dr. Koopman as the principal investigator, he had 2 other people on his team who also did some previous research for the FAA and joined with Dr. Koopman on data bus evaluation criteria. The 2 people are Kevin Driscoll and Brendan Hall. Mr. Kevin Driscoll is a fellow with Honeywell's Aerospace Technology Advanced Technology Labs. He has over 40 years' experience in safety and security critical systems, including the development of systems for many commercial and military aerospace vehicles. He was a principal designer for several communication standards and led efforts for adaptations of commercial standards to aerospace. Mr. Driscoll has over 40 patents issued and a dozen more pending for safety, security, and real-time applications. Mr. Brendan Hall is a technical fellow for Honeywell Aerospace Electronic Systems Advanced Technology Center of Excellence, Minneapolis, Minnesota. He has over 20 years experience in research and/or technology development in the area of systems engineering for large, complex, safety-relevant real-time systems. He holds over 30 patents and has published numerous papers related to fault-tolerant communication and model-based design. We'd like to welcome Dr. Koopman, Mr. Driscoll, and Mr. Hall.
Hi, everyone. I'm Phil Koopman. Thank you for the introduction, Barbara and Chuck. So I'm Phil Koopman. I'm the principal investigator. I want to acknowledge right now that Kevin and Brendan from Honeywell have done a whole lot of work on this. But I'm the one who gets to do the presentation today. I know they're on and can participate answering questions at the end. I have quite a few slides. Right now, if you want, go to that URL in the upper right of this, checksumcrc.blogspot.com, and you can download a copy of the slides I'm showing today there if you want to refer back to something for questions and so on. So they're there now. You're welcome to download them. And there'll be as mentioned earlier, there'll be a copy of this video available in the course. Today I'm going to be talking about background, introduction, and results summary. I'm going to talk about a high-level comparison among checksums and CRCs. There's some industry survey results, So I'm talking about system-level effects and interaction, things that sort of go beyond the strict definition of checksum and CRCs, and especially mapping the criticality levels. Given that you have a CRC, how do you fit that into the context of a higher-level safety argument? And it's not going to be a one-size-fits-all answer, but it is going to be a methodology that shows you how to do the appropriate argument. At the end, there'll be discussion and Q&A. And I probably am not going to talk about every word and every single slide. They're more in the nature of a very rich set of notes. I'm going to hit the high points and the details that I think matter, and that hopefully more time for questions at the end. So we started this a couple years ago. This is the project overview was to compare CRC and checksum performance and answer questions like which algorithms are better, how many error coding bits do you need, what kind of error detection coverage are you going to get, and how do they map to functional integrity levels. The specific statement of work goals for this work were to do a literature review, study the CRC parameters and functional integrity levels, study the checksum parameters and functional integrity levels, and make recommendations, suggestions for future work. There is a final report that's in the final approval and publication process, and it will have an extensive literature review, which is beyond what I'll be talking about today. We've already mentioned the investigators, myself, Kevin Driscoll, Brendan Hall. Our rules were mostly that Kevin and Brendan did the industry interaction and proposed the approach for fitting this data into a discussion of system safety, and more to do the raw analysis of data and be the coding expert. So some background to get everyone on the same page in terms of terminology. We're talking about the ability to take a data word, so bits of data, and it could be on media, it could be in memory, it could be on a network. We don't really care where, with a couple exceptions to get to. So there's some data, and then after the data there's a check sequence, and the check sequence is a set of redundant bits that goes after the data to help you detect errors that have happened. And so you can think of it as a hash word. It's just some mixing of the bits. The simplest one we've all run into is parity, which is just a one-bit XOR of everything, and that detects some errors, but certainly not a lot. And so in general, the bigger the check sequence and the better the hash function, the better error detection you get. With the one caveat that purely random is actually not ideal. You want structure in it to help with low numbers of bit errors. In order to use this, when you take a look at a piece of data, you look at the data, you recompute the checksum or CRC or other error detection code, you check that result against the check sequence. If they do not match, you know there's an error. If they do match, then one of two things has happened. Either there's no error and you're happy, or there's an error you can't detect, because eventually there's going to be some error you can't detect. And that's where the problem is. What do these undetected errors look like? There are two common approaches to hash functions, really the ones we're going to talk about today. One is a checksum, where you add up chunks of data words. Often it's bytes, but it could be words, and I don't really want to get bogged down in that, so I'm just going to call them chunks. You add up chunks of data words and you put them in the check sequence. Or CRC, which is a linear feedback shift register, and we're going to talk in more detail about that. What you want is really good mixing to detect many combinations of bit errors. We have some terminology, the undetected error fraction. That's how many bit errors that are undetectable under a certain set of assumptions. You can never detect every possible error, but what you can do is you can weight the undetected error fraction to be 0 for small numbers of errors and low for errors. What you want usually is good error detection properties for small numbers of bits, and the reason for that will come out at the very end when we see what the implications at the system level are. So we're going to concentrate on a thing called Hamming distance, which is the minimum number of bit errors undetected. So if you have a Hamming distance of 4, for example, that means 100% of 1, 2 bit errors are detected, but some 4-bit errors are not detected. Hamming distance of 5 would pick up all 4-bit errors. Hamming distance of 10, not that we're going to see that today, would be all 1 through 9. You get the idea. So when I say Hamming distance, that's the first number of bit errors for which some of them are going to go undetected. Some more terminology. Error coding is a generic term for it doesn't matter how you do it. It's just computing something and storing it to detect errors. Checksum has to do with adding data chunks. A CRC is an error code based on polynomial division over Galois 2. I promise I'm not going to talk more about that. If there's plenty of stuff on the web if you want to get into theory, But I will show a picture in hardware and give you some intuition about it. A polynomial is a CRC feedback polynomial, and it's called that because of this mathematical basis on polynomial division. But a lot of people call it the feedback terms for the CRC. The math for CRC and the math for linear feedback shift register are the same. Those are commonly used in pseudo-random number generation. So if you don't know one, you know the other. It's really pretty much the same stuff. And one thing about the polynomial is because it is a polynomial, you can have prime factors, and you can say, let's divide it into prime factors. It's really it's close analogy to integer division, and I'm not going to worry about the details of this presentation. And it turns out that what factors you have when you divide up a polynomial into its prime factors affects the error detection capability, but perhaps surprisingly not as much as a lot of people think. So we'll be talking about that a little bit. Finally, the code size is the number of bits in the error code result. And so going back a couple of pages, you have the code word, which is all the data, and you have the data word, which is the data you care about, and the check sequence. The code word is just both of those put together. Okay, in terms of error detection effectiveness, Hamming distance we talked about before, but I'm hitting that again because it's really important. The minimum number of bit errors that is undetectable. There's a thing called Hamming weight, which is the number of undetectable errors per given number of bit errors. So if we had Hamming distance 4, then all 1, 2, and 3-bit errors are guaranteed detected no matter what. And at 4-bit errors, there may be 10 or 20 or 100 or 100,000 different distinct patterns that are undetectable. And the number of undetectable patterns is the Hamming weight. But after you get off the Hamming distance, what fraction of things do you not detect? And it varies depending on the code. It can be small, it can be large, and that's another property of the code. There's bit error ratio, and the thing about bit error ratio is that's how we're going to look at how likely it is bits are going to flip. So we're going to use a bisymmetric conversion error model, and that means bit flips loosely, and we're going to assume random independent bit inversion. So we're not going to assume there's no particular pattern. The hardware is not influencing that. And so based on those kind of random bit flips, maybe 10 minus 6 means 1 out of a million bits going to flip. And based on that, we're going to have a probability of undetected error, PUD, which assumes some bit error rate and assumes some particular code. And even if they're very small, even if it's a PUD that's very small, there's a whole lot of messages, there's a whole lot of data, so they add up. There's the notion of a burst error. We're only going to talk about that a little bit, and it's an arbitrary corruption of k consecutive bits. It doesn't mean they're all flipped. It just means some of them are flipped, but there's no which pattern. And we're going to talk about an error check, which is the process of looking at the code word and deciding if the data word matches the computed value of the check sequence. Okay, I'm going sort of fast through the intro, but I want to get to the results. So here's a classical CRC overview. It's a cyclic redundancy code, and a lot of people have seen it in hardware form. And you can think of this as a shift register, where you have a running total that starts with some number, often 0. There's a seed value that it starts with, and you shift in the message or the data. So the data word gets shifted in 1 bit at a time and comes back, and there's little XOR gates interspersed in the middle of the shift register, and the position of these XOR gates corresponds to the feedback polynomial. So this hardware is really doing polynomial division, and the remainder of the division is the result of this CRC, more properly a check sequence. And here what you do is you look at the message payload. If it happens to message, you run the message through this hardware register. Whatever's done, put in the CRC. The receiver runs it through the same register and decides if the computed remainder value in the register matches the CRC value. If they don't match, you have an error. If they do match, you either have no error or you have an undetectable error. And undetectable errors are terrible. Now, CRCs has been around for a really long time. And people say, gee, you would think after all these years, the best CRC is a well-solved problem. And unfortunately, it isn't really. When this stuff came out, they didn't have the compute power to look at all the possibilities, and so they used some math, and they took some nice guesses, and they came up with some okay stuff. But until fairly recently, the compute power was just not available to do an exhaustive search. And it turns out that using mathematical analysis doesn't get you all the results you want. You really have to do an exhaustive search to get there. And that's some of the work we've been doing for a few years. The other problem is the literature is poorly accessible to computer engineers, computer scientists, people who are not specialized in it. A lot of it's written in dense math that's hard to apply. A lot of it is just used in uses terminology that engineers look at it and say, I'm not sure what to do with that. So as a result, practitioners mostly use what someone else used, and they assume it's good, and that turns out to be a bad assumption at the time. And they're unaware of limitations or mistakes in previous work. And I'll give you some concrete examples. And also the practical application is poorly documented. There's really a handful of guys, mostly originating in the European rail domain, who kind of know this stuff, and the information just isn't out. So the purpose of this project was just as much to find out what the good technical answers were as to get the information out in full form. Here's an example, and this is an old version of Numerical Recipes. Some of you may have seen Numerical Recipes C. It's a pretty classic book. There's a new version out, so this isn't the old version, but and so I'm not saying they're wrong now. I'm just giving an example, and I don't want to give them a hard time because this was just representative of what used to be out there years ago. So they say, we're going to pick a CRC, and it says it's based on primitive polynomial of degree m. It turns out that primitive polynomials are not always the best. Alternately divisible by x plus 1 plus x. It turns out that a lot of times doing that is a bad idea because it doubles the error detection rate for even numbers of bits. You get odd numbers of bits for free, but no one ever talks about it. Doubles the undetected error rate for even numbers of bit errors. And sometimes that's actually making it worse. In that same paragraph, they say, well, you could use the CCITT polynomial, which is really well known, or you could use the CRC one, and they just, it's like a beauty contest. Go ahead and pick one. And some of them are good, some of them bad. Some of them are good for some places and bad for others. It's the example of that. And at the end, they have CRC12. It turns out that this is incorrect. There's a missing plus x square. The authors didn't know it till I was double-checking sources and found out, their CRC12 is different than everyone else's. So who knows how many pieces of code are out there using this incorrect CRC, and it's actually a really bad one. Now, to their credit, the authors fixed that problem in the 3rd edition based on some email I sent them. And they have a table of primitive polynomials that they said, well, these are the ones we know about with no evaluation whether they're good, bad, and different. So you just can't pick this stuff from a random list. You actually have to know which ones are good and which ones are bad. That information was totally unavailable until fairly recently. Several researchers have worked in this area, and you had to go to specific publications to find them, and they were hard. They were really hard to access. And so one of the points of this project is to help change that. Here's an example. This is for 8-bit polynomials, so 8-bit CRCs, and all these pictures, this probability of undetected error. And what you're going to see is going up is worse and going down is better because you want the lowest probability of an error getting by you without detection. And what this dotted line is a theoretical bound. So we went through every length of message and said out of all 256 possible polynomials, which one is the best? And so each one of these is potentially a different polynomial on this thing. And so that's the theoretical bound. You for sure cannot do better by exhaustive search, but you can certainly do worse. So let's take an example. The dark data radio channel. Now this is a standard found on the web. I don't know a lot about it other than I saw it, but they picked the polynomial of 0x9c, so hexadecimal 9c. That tells you the feedback taps for that polynomial, and it's a particular notation. In our notation, the +1 is implicit, and the 9 is the highest bit being set. And you can see that is optimal down to about 8, 9, 10 bits down in there. It is optimal. You cannot do better. And then it falls apart. So you win down at 8 bits. You get Hamming distance to 5, which means you're detecting all 1, 2, 3, and 4-bit errors. And then it's just terrible because the Hamming distance to and actually quite far away from the bound and anything longer. Well, where are they using it? They're using it in the range of 16 to 48 bits. So it's actually one of the worst polynomials you could pick for that application, even though it's ideal at shorter length. So what you see is you can't just pick, oh, this is a really good polynomial. So part of the question is, well, where is it good? And is that where you're using it? And so these guys seem to have picked a suboptimal polynomial. Again, I don't know the standard. There might be something I'm overlooking. but it's an example of this is the kind of thing you don't want to do if what you really care about is some other data payload length. There's a thing called CRC8. That's one of the published standard quote-unquote CRCs, and it actually does a pretty good job. It's not bad for intermediate length, but it actually, above size 85, you could do a lot better. There's another CRC that gets into this corner, Hamming distance 4 corner. So if you have a payload length or a data word length that's above 85 bits, what you're going to find out is CRC8 is terrible, and you could have done a lot better. The question is, can you do better? Is there one better? Well, you can use Bycheva. This is one of the previous research publications I mentioned. Bycheva has a polynomial called C2, the hexadecimal value of 9.7, and it gets right into that corner. And so you basically always want to use that one instead of CRC8. It's always better, and at every possible length, and it gets into that corner. Well, there's another corner here. There's a Hamming distance 3 corner. What if your data payload's above 128 bits, and you want to do better than the Bycheva polynomial? Well, there's another one that we found and published with a different hexadecimal value of A6 that gets right into that corner. So now you have a choice. If you want things around 60, 70, 80-bit payloads, you really want the Bycheva polynomial. But if you're up at 150 or 200 bits, you really want the new polynomial that we found and published. So the moral of this story is, or the morals are severalfold. One is, just because someone else is using it doesn't make it a good idea. Just because it's a published international standard doesn't necessarily make it a good idea. Just because it's optimal for some length doesn't mean it's what you want to use. You have to look at what's good or optimal for your length, for your particular situation. Okay, so that hopefully is some motivation for why this kind of thing matters. Basically a lot of the stuff out there is suboptimal or just plain wrong, and want to fix that, and several authors are also helping to fix that. We're not the only ones, but there's still a lot of bad information out there. So we did a literature survey to identify candidate codes and candidate evaluation criteria, because it's not so clear how you say which one is best. We looked at the aviation industry to look at data characteristics, usage scenarios, fault exposure, things like that. We analytically evaluated the error code effectiveness for both CRCs and checksums. It turns out that CRCs are actually easier than checksums for reasons to get into, having data patterns. And originally we mapped effectiveness onto DO-178B software levels. What we really did is a little finer than that. So if you notice this, that's not quite right. We'll get to that. But the idea is to show you how to map this effectiveness into a way that you can use to evaluate your system in terms of safety. And we identified future work. Let's jump to the project results. Here's what we found. High-level results. It's all about the Hamming distance. What matters more than anything else is the Hamming. If you have a good Hamming distance, all things being equal, and I know they're not always equal, but all things being equal, you want to go with the best Hamming distance you can get. If you have a bit error rate model, the number of 100% detected error bits dominates everything else. And when we get to the examples, you'll see why it's based on the math. For anything realistic that has moderate to low error rate. And CRCs do much, much better than checksum, pretty much always. I know they're a little slower to compute, but they really have a much better Hamming distance. So what we saw in industry surveys was mostly the use of CRCs, but they were usually the standard polynomials. And what was happening was, in a lot of cases, they were okay, but people were leaving 1 or 2 bits of Hamming distance on the table. By that, what I mean is, for the exact same computational cost, they could have had 1 or 2 bits more of error detection just by changing the CRC column. There were a few near optimal and a few problematic examples, and we'll go over those. No names, no places, but we're going to talk about some of the kind of things we found, give you an idea of what was out there. And we're going to talk about mapping to criticality levels. There is no one-size-fits-all answer. But so instead of saying always use this polynomial or always go for Hamming distance 6 or something like that, those are not the answers we found. What we did find was a way to propose a methodology where you could go down a flow chart, make decisions, and come up with something that's right for your system. And it's going to be based on the system's data word length, the bit error rate, the fault containment you have, secondary effects, and then you can select an error code based on ultimately giving you the Hamming distance you need for your system safe enough. The starting point for this was a literature survey that I'd done with a student back in almost 10 years ago now. And what we did was we said, let's just look at small CRCs. Let's look at up to 16-bit CRCs and try every possible one. So for a 16-bit CRC, there's about 2 to the 15th possibilities, and it turns out that half of them, if you do a bit reverse, you get the same properties. So we had to look at about 2 to the 14th possibilities. That's still quite a few. And we tried them all, and we tried them at every length. And what we got to was this table. The way to read the table is, if you want Hammond distance 5, for example, you read across the Hammond distance 5 row. And if you have a data word length of let's make it 120 bits, you read across and say, well, a 14-bit CRC is only good to 113 bits, but a 15-bit CRC will give you Hammond distance 5 up to 120 bits, and the polynomial right there, 6A8B, that's the polynomial. So this is an optimal selection polynomial. The underlined ones are previously published polynomials. And what you can see is a whole bunch of them have not been previously published. And notably for size 8, the optimal one hadn't been published previously, and for size 16 also. Some of these, you see 2 of them are underlined and the rest are not. So there are a lot of CRCs that people didn't know were good, or you had to read the one right paper and find the paper to know they were good and not uncommon use. So this is the kind of results we were after. We wanted to scale it up, and we wanted to compare against alternatives. Now, checksums are tougher. The difference is in CRCs, the data value does not affect the error detection capability. I'm going to say that again because it's important. In CRCs, the data value does not affect error detection capability. So when you flip the bit, it doesn't matter what the data pattern is. The CRC will detect the bit flip regardless of the data pattern. Checksums are not like that. Checksums, the data patterns and the bit flips interact via the carry bit in the addition part of the checksum. And so the only way to get a handle on checksums is to try not just all combinations of errors, but all combinations of errors and all combinations of data. And there just isn't enough compute power to do that. So for CRCs, we got analytically exact results by trying all possible combination of bit errors. That still takes a long time. We have some pretty intense optimizations, but we did. When you see a CRC result, it is exact. We checked every single possible combination. For checksums, we couldn't do that, so we ran at least a billion trials, a lot of times a trillion trials of random data and random checks, just random data and random bit flips to get an idea. Pretty much we always made sure we had at least 1,000 undetected error events. And if we said a checksum has a breakpoint going from one Hammond distance to another, we did at least 1,000 potential data points worth of trials at that other length. And so that means when you see a checksum value, it's not a guarantee that's where the Hammond distance change is, but it's our best shot, and it's likely if it's not that, it's close. And I'd like to have a more exact result. That's going to figure in ATN 32, but given computational resources, that was the best. We compared the results against published results, so everything except ATN 32, which I'll get to in a minute, has been compared against every published result we can find. And the reason for ATN 32 is we didn't find any published results. Okay, getting to the results, the checksum results. And this is sort of the summary version, but here's where it turns out. The checksum performance is data dependent, and the worst case tends to be 50% 1 bit and 50% 0 bit. This had been previously published in a journal paper I'd done with another student, and we just reconfirmed it independently. Got the same answer. And the insight here is that when you're in a checksum, you tend to miss errors when you have some combination of carry bits across the columns of bits appearing someplace and disappearing other places and canceling each other out. And that's most likely to happen if your data is half ones and half zeros. So if you're doing checksum performance, don't try it on an all-zero word. That's the best case. Try it on a random mix of 50% ones and zeros. And so all the results we publish in these slides are for that worst case. There are also traditional checksum results, LRC, which is just an XOR of all the data chunks. 2's complement addition, that's normal computer addition. 1's complement addition, which means that you have a +0 and you have a -0 and you're symmetric around that. Really old computers used to do that. but it turns out to be better for checksums, but still used there. And you can think of that as wrapping the carry out of the addition on 2's complement back into the low bit. You don't throw the bit away. It gives you a little better performance. And a Fletcher checksum, which is a well-known combination, what you do is you do 2 1's complement checksums on high half, low half, and then the second one is a running sum, and it turns out to be better Hamming distance than a regular checksum. So those are all well known. They're out there. They're in use, and we just wanted to compare them. And so you're going to see results graphed based on bit error ratio, and so it's going to be the probability of undetected error based on that, on a particular bit error ratio. And here's the first example. Remember, up is bad, down is good. And you can see for LRC, longitude and redundancy check, at 2's addition and 2's complement addition and 1's complement addition, they're all pretty much on top of each other. The LRC is worse. It turns out the 1's complement addition is actually quite a bit better, but on a log-log scale like this, you can't tell the difference. And you can see Fletcher checksum is a whole lot better. It's much further down. So if you have to do a checksum, you want to be doing a Fletcher checksum. It's going to give you a whole lot better error detection. And the PUD, so we have a PUD of per message. If you have perhaps up to 10 to the 9 messages per hour, we're getting 10 to the minus 9 per hour is down at this red line. So Fletcher achieves Hamming distance 2 or 3. Let's switch it into how Hamming distance plays into this. So this is 8-bit Fletcher, 16-bit Fletcher, 32. And when I say 16-bit Fletcher checksum, a 16-bit Fletcher checksum is 2 8-bit sums concatenated. So the FCS is a 6-bit FCS. And what you can see is for short data word lengths, and these are in bytes on this diagram. For short data word lengths, any of them are fine, but as soon as you get up to just a handful of data words, but Fletcher 8 runs out of steam, it goes up to Hamming distance 2. To get Hamming distance 3, you want to be at Fletcher 16, up to about over 100 bytes, and then you want to be at Fletcher 32. And so the idea is that the longer the data word is, the more bits you want in the FCS, which kind of makes sense. But Fletcher checksum only gets you Hamming distance 3 on a good day. And people say, oh, Fletcher checksum is Hamming distance 3. Well, only up to a certain length, and it's up to you what the length is. And you can see none of these get you up to about 10 to the minus 9 per hour, because that's the bottom exit. I also looked at ATN 32 checksum, and so this is from AN 466. I'm not going to go into details, but you can go look it up and see how they're using it. It smells like a Fletcher checksum. But instead of 2 16-bit 1's complement sums, it's using 4 8-bit sums. I don't know the reason why they did it, but I can speculate it has to do something with computational efficiency or something like that. But this is what they chose. And it turns out the performance is actually quite a bit better than Fletcher checksum 32 bits for short word length. In fact, it picks up a Hamming distance of 4 up to a certain length. The catch is that it pays for it by going up to Hamming distance 2 quite fast. So at about 760 bytes and above, it's at Hamming distance 2, whereas a 32-bit Fletcher checksum has still been at Hamming distance 3. So you can see this red line, Fletcher checksum 32-bit stays at Hamming distance 3 all the way across, and then ATN is very, very good at short message lengths, but gets dramatically worse. Remember, this is a log-log scale, so that's a big gap. And at and above 760 bytes, now remember my caveat about the results, anything I say is Hamming distance 2 is for sure not better, but down in this corner there might be 1 or 2 bytes where I just didn't have to see the undetected 2-bit error. But the problem is that the maximum ATN payload, as I understand it, is 1471 bytes checksum, and so what's happening is if you're running small payloads, it's going to actually be better than Fletcher checksum, but for large payloads, it's going to be pretty bad in terms of getting a low Hamming. So if you're using ATN, that's something to know. You don't really want to use it above about just under 760 bytes. You don't really want to use it above there unless you know what's going on. By contrast, CRC32, so this is the IEEE 802.3 polynomial that's just used everywhere. CRC32, you can see, is much better than all of them. And again, I understand that CRC32 takes more computation time, but you're getting significantly better Hamming distance and error detection. And in particular, I've annotated it. You can see that CRC32 is getting 1 or 2 bits better than ATN32 or Fletcher checksum. So it's always doing better all the way up until here, where they're both Hamming 3. But even at the same Hamming distance, CRC32 gives much better error detection. Remember, I talked about Hamming weight is the fraction of undetected errors. So CRC32 and 32-bit Fletcher checksum have the same Hamming distance up here on the right, but CRC32 has a much lower Hamming weight, meaning it detects a higher fraction of all possible errors. So from those charts, you looked at the undetected probability of undetected error, and it's all about the Hamming distance. If you tell me what the Hamming distance is, I can tell you whether it's good or bad code, and the only time that anything other than that matters is when it's a tie on Hamming distance. We can see that here, CRC32 always has a better Hamming distance except here, and then it has a better Hamming weight. They're both at Hamming distance 3, but it just happens to have fewer undetected errors. So Hamming distance is a dominant factor. If you have random independent errors, that's what matters. And the reason is, for a given message length, the shorter the message length, the less likely you're going to have errors at a particular bit error rate. But for a fixed message length, as the bit error rate increases, the higher the bit error rate, the more likely you're going to have multiple bit errors in that message. But for any reasonable bit error rate in which the network's actually going to work, if you have an error in every message, the network's just not going to work. If you have a reasonable bit error rate, the chance of getting 1-bit error is a whole lot higher than the chance of getting 2-bit errors. And 2-bit errors is a whole lot higher than getting 3-bit errors, so eventually it's just really unlikely to get a lot of errors. So a Hamming distance that knocks out and detects all possible 1 and 2 and 3-bit errors is going to get you most of the way there, just because the large number of errors just never happen. And so that's why Hamming distance tends to be the dominant factor for this kind of fault. Here's another way of looking at the data. And so this is where they have Hamming distance. So we don't need the graphs anymore. All we need is a table showing us where the Hamming distances are. And you can see from this table that CRC32 is going to have a nice high Hamming distance up to, in bytes, 11K bytes, compared to 504 for ATN32, and it gets Hamming distance 5 here. And so you can see that it's going to do a lot better. So higher Hamming distance at longer data word length is better. And so you can see that's why, this is one reason why you want to use CRC32 if you can afford the computational cost. Now, given CRCs, we could say, well, fine, let's use CRC32 for everything. Well, not so fast. CRC32 is actually not a bad polynomial as such things go. I've certainly seen worse. But if you have a particular application, if you're not saying, I just want a general purpose one, so I don't have to think, I'm just going to pick one. If you actually want one that's tailored for a specific application, we can dig in deeper. And on the left, we see a picture where, for a particular data word length, so the x-axis is going between 10 and 1,000 bytes, that's logarithmic, that 802.3, which is CRC32, does 1 bit of Hamming distance worse than a particular polynomial. And so if you're in this window in the middle of the left-hand graph, you really want that other polynomial. You're going to get another bit of error for free. On the right-hand side, you can see the orange one again is CRC32, and there's another one, the one that starts with hex 4 and so on, that gets you another bit of Hamming distance across this length in 2 places. This has to do with that staircase diagram. So you can do a whole lot better. Now, I mean, do you want to do better? Well, if your current CRC32 is giving you enough Hamming distance that your system is safe, that's okay. But if it's not, or you just say, hey, we are at liberty this design to be able to pick whatever CRC we want, why not pick the one with better Hamming distance? So in those cases, you may want to go with a different polynomial than standard CRC32. So here's the table of good choices, and again, you can download these slides. I'll have the website again at the end to get this data. And so what it says is for 16-bit CRCs, here's what you want to use. This is an extension of the table we saw before. And these are also good choices for 24 and 32-bit CRCs. So in every case, these were picked to have the longest possible data word length for that particular Hamming distance. So there might be better polynomials if you have a shorter data word length, but at least this guarantees you're getting the maximum Hamming distance you can, or it tells you for sure if there's nothing on this table, then it's not possible to get that Hamming distance at longer length, because this is based on checking every possible. Okay, switching to the industry survey results. What we did, the folks at Honeywell did all the legwork on this, so I give them full credit for this. We sent a survey out to industry through our contacts at FAA, and so we did not actually see the responses ourselves. Responses came back through FAA, and they scrubbed the company information and any identifying information. So we have no idea who the respondents are. There's no way for us to reverse engineer what was going on, but the FAA vetted that these are real responses from real contacts that were appropriate to include in the survey and in our study. We got 15 responses back, and we basically asked for what the characteristics of the system were and how they were doing error detection. We got 9 memory applications back. All of them are CRCs, and some have additional error detection discussed later. We got 6 communication applications back, and 1 had a checksum, 4 had CRCs, and 1 had a dual CRC. I'll be talking about these. I believe that the scrubbed information can be available. That's up to the FAA to decide whether to make it available, but it was, in theory at least, it can be done if they approve it. The industry memory responses were somebody who was using CRC16 IBM up for 64 kbytes, and that turned out the same Hamming distance as an optimal CRC, but they could have done 1.87 times better on the undetected error fraction on the Hamming weight if they'd used another polynomial. So that's not a huge deal, but it's kind of nice to know whether you got it optimal or not. The other CRCs use the IEEE 802.3 polynomial, the one I showed you the graphs for, the standard Ethernet polynomial. And pretty much all of them, in fact, all of them could have gotten 1 or in some cases 2 bits better Hamming distance by using an optimal polynomial. Same computational cost, all you do is put a different bit pattern in when you compute your CRC. If you're using a table lookup, you have to compute no tables, but you know, it's really no big deal. It's the same compute cost. And so what we found was people were going with the commonly used one, and again, if that's providing them the Hamming distance they need, then they're fine and there's no problem. But they were leaving Hamming distance bits on the tables they could have gotten at the same cost. For the communication responses, one of them was a 1's complement 8-bit addition checksum for mostly 64-bit messages. If they'd used a Fletcher checksum, they would have gotten 38 times better error detection fraction for a modest computational cost. If they'd used a CRC, they could have gotten Hamming distance 4, and so they basically could have gotten 2 more bits of error detection. Now, that might be the right trade-off for them because maybe they had a computational resource limit, but it was interesting to see that you know, they could have done better. And again, I'm not Monday morning quarterbacking on this. They made the decisions they made. But if you're in that kind of situation, it's kind of nice to know what the alternatives are and then decide which one is appropriate first. One used a 24-bit CRC for 2,000-bit plus message at Hamming distance 4. They could have gotten 1 bit more Hamming distance at the same cost for the CRC. And if the max message length wasn't critical, a lot of times in embedded systems you see the small messages are critical and the large messages almost never happen and aren't critical because they're data transfers and that have their own integrity check inside anyway. If that was the case, you can actually get Hamming distance 6 up to 2024 bits. There's a protocol to TTP that actually does that with a particular polynomial. There's a dual 16-bit response I'm going to get to. The other CRCs were 802.3, and again, they left 1 or 2 bits of Hamming distance on the table. One response indicated an incorrect 802.3 polynomial. Now, I don't know whether this is a typographical error, whether the person looked at the code and copied the wrong value out, or whether the code itself was wrong. And I don't know, but this raises an important point that I've seen in my own practice, that people write up CRC code and they don't test it. And if they don't test it, they might have the wrong CRC. They might have that typo you saw in numerical recipes. They could have whatever. And they have no idea whether it's working or not. And the only way I found that works to test it is to actually do fault injection experiments, flip some bits, and make sure you're getting all the bit error detection you expect to be getting. Some folks use multiple error detection techniques. There was a single error correction, multiple error detection code plus CRC on memory. There was small CRC on memory blocks plus large CRC in all memory. Parity plus per word plus the CRC or checksum, 2 CRCs and a checksum. We're going to take a look at a couple of these, but this is out there and it certainly doesn't hurt. But what we found is generally you can only take credit for the better of the 2 techniques. There are several cases where people had 2 techniques and they might have thought that that really made things better, and it turned out it didn't change the Hamming distance at all. The one thing we did find was that if you have parity per word, then a checksum and a CRC come out at the same Hamming distance, because the parity per word means you have to have 2-bit errors in a word and then another 2-bit errors in another word to get past the checksum. That was particularly effective. But a lot of the multiple ones we've seen, they reduce the undetected error fraction, but they don't actually help the Hamming distance at all. So I'm going to go to some particular examples. ARINC 629, which is an aviation-specific protocol, uses parity plus per word plus a checksum. And you can either pick a 16-bit CRC or you pick a 16-bit 2's complement checksum. And based on what I've said, you might expect that the CRC beats the checksum, but it doesn't quite turn out that way. And that's because this has the per word parity I was talking about. The CRC gives Hamming distance 4, but the parity doesn't help because it turns out that you can get bit errors that get past the CRC, so the parity doesn't increase the Hamming distance. I actually wrote a simulation. I did random fault injection, and I found that there were bit patterns that basically, there are 4-bit errors that get past. The 2's complement addition requires the 2 errors to be in different data chunks, but the data chunks each have parity, so that means you actually need a total of 4 errors. 2 of those errors have to be on parity bits, but 4 errors will get past it. So the net result is Hamming distance 4. So perhaps in a surprise, in this case, CRC and 2's complement checksum give the same Hamming distance. The CRC gives better undetected error fraction as a lower Hamming weight, as you might expect, but they both got the same Hamming distance. So that's kind of interesting. We had another response that had multiple CRCs. It is very common for people to say, well, I'll put in 2 16-bit CRCs, and I've seen people claim that 2 16-bit CRCs is as good as 1 32-bit CRC. Sometimes they use arguments based on polynomial factorization math. I haven't seen yet a system where that actually turned out to be true. There have been several attempts at it, and I end up having to review the papers on these when they get submitted, and all the ones I've seen so far, it turns out not to really work. There was an industry response that used 2 16-bit CRCs. We had enough data to take a look at it, and it turned out one of the 16-bit CRCs was Hamming distance 4. The other one had a worse Hamming distance. They were designed to avoid common factors, but basically we were able to find 4-bit errors that got past 4, got past both the CRCs. So the second CRC improved the probability of undetected error, meaning that just based on randomness, you still had to get the random match. So it reduced the undetected error fraction, but it did not change the Hamming at all. And that's often what you get with using multiple small CRCs. In contrast, the 32-bit CRC probably could have done a whole lot better. There's some memory-specific CRC properties. We're asked to comment on this specifically. If you have a memory array, you can have multi-bit errors from single event upsets could actually scramble a bunch of errors next to each other because they could be memories in rows and columns, and they could be 1 row apart. Now, which bits they hit depends on the interleave strategy, so there's nothing in general we can say. Interleaving means that the memory bits don't come out in the exact order of the columns. You scramble the columns around to reduce the probability that adjacent bits flip will happen to be in the same memory word. So you need detailed physical information on the memory to actually give a specific result. But there's a CRC property that helps, and this is one I've not seen published, so it's worth mentioning. CRCs usually have multiple regions in which they're good. If you pick the right CRC, for example, this CRC 9002-2004, and if you use it on a 4 gigabyte memory image, what you find is it gives you Hamming distance 2 for the entire image, which is the best you can do. But it gives you Hamming distance 4 for all multi-bit errors within a span of just under 2 to the 16. And it gives you Hamming distance 6 for all multi-bit errors just in a span of just under 2 to the 15. So this might be a very attractive CRC because if you have multiple bits clustered together within those bit ranges, the CRC will simultaneously give you all these levels of protection. Obviously, it only gives you one at a time, but it's a good way to get protection for the whole memory image and at the same time get increased protection for the more likely errors they're going to have clustered close to each other. Okay, I'm going to switch to system-level effects and cross-layer interactions. Again, this is the work primarily done by Honeywell. There are some of these things are I've learned, some things they've learned, but we're going to get to the methodology after this. One thing to think about when you're looking at using CRCs is that how you use this CRC can be undermined to the point that the CRC is almost useless. And a classic example, this showed up in HDLC, it shows up in several communication protocols, is that if you get an error in the length field of a message and make the length, instead of pointing to where the CRC is, it points to the middle of the message, you will then grab data out of the middle of your data field and use it as your CRC. Now, it only takes a 1-bit error to change this length field. You just flip one of the length bits, and now you're looking in the wrong place for the CRC. But by doing that, you've lost all your mathematical guarantees because you're just taking some piece of data. And if it's a 16-bit CRC, there's a 1 in 2 to the 16th chance, 1 in 64K chance, that this piece of data will just happen to be the right CRC for the modified length field, the data up to that modified length, and then it thinks that this is CRC here, and there's 1 in 2 to the 16th chance it'll match. In other words, Hamming distance graded to 1. If you want to solve that, then you either need parity on the length field, which Errant 629 does, or you may assert that an incorrect length message will always get caught. Many protocols do this, but if you care about safety, you want to make sure that assertion is correct. I mean, I would check with corrupted length fields and make sure it really works. And some of them, FlexRay, which is a safety critical automotive protocol, actually puts an independent CRC in the length header field to make sure that the length field hasn't been corrupted before it goes and looks up the CRC for the payload. And given a choice, this is how I would design a protocol. And here's a picture of how FlexRay does it. So it is a frame ID, which is the message header, the message type, and the payload length, and there's a header CRC protecting that, and that way it always knows that when it looks for where the CRC is, that it's doing so on uncorrupted data to the same level of integrity as the payload. So if you have Hamming distance 6 CRC on the payload length and then Hamming distance 6 CRC across the data payload. And that's how they make sure that they actually get the right amount of protection. We also found some other things, and again, these are not CRC problems per se, but rather how you use the CRC causes issues if you don't use it quite the right way. And this is in Errant 625, which is a controller area network applied to aircraft. And what they did, and I'm going to simplify it, but what they did was they took the CAN standard and said, that's a great automotive standard. The chips are all over the place, the tools are all over the place, and it's used for automotive, so let's build on it and add things to it. But they didn't change the underlying standard. Well, as it turns out, the underlying CAN standard has a vulnerability to bit stuff errors. And I'm not going to do the foregoing detail, but what happens is, here's a bit pattern, and what can happen is if a 0-bit gets changed to a 1-bit, that later changes what used to be 0-bit into a stuff bit. The stuff bit, the transition's added after every 5 of 1 in a row to make sure you see an edge so you can keep synchronization of the receiver. And if you have just the wrong bit pattern, something that required a stuff bit all of a sudden gets changed to a data bit, and the stuff bit shows up as the data bit. What you have is conservation of number of bits. So 2 errors, 2 bit flips cancel each other out. They leave the message the same length. There's no stuff bit violations, but what's happened is all the bits in the middle basically get shifted 1 bit earlier. And so this results in a 2-bit error looking like an arbitrarily long multi-bit error that gets past the CRC. I actually ran some data, and the short version of this data is that you had Hamming distance 2 in a CAN. This is just the data word length. You only get Hamming distance 2. We found experimentally lots of ones that get passed. The undetected error fraction is about 3.3% of errors that would be undetected by a good Hamming distance 2 code. So if you had a Hamming distance 2 CRC, this is about 30 times better, and the reason is there aren't that many data patterns that have that stuff bit vulnerability. You have to have the right data set up for this to happen. But it happens apparently 3.3% of the time. So given a 2-bit error with random data, you're going to get Hamming distance 2 a lot of the time. So what's the bad news here is if you're using CAN, and this applies to cars and applies to anyone who's using CAN, if you were counting on Hamming distance 6, which is what CAN advertises, you're in for a surprise because you're only getting Hamming distance 2. Now, if Hamming distance 2 is good enough, you're still okay. But if you needed more than Hamming distance 2, then you've got a problem, and you have to somehow deal with that. Now, ARINC 825 actually has another thing, a high-integrity CRC. So this is a CRC value that they plop down into the payload, and the idea is to give you better than the CAN CRC. It turns out that, unfortunately, this CRC is vulnerable to the same bit stuffing effect, so it doesn't get past it because this is also in the bit stuff field. But when I reviewed the standard, I found some things that didn't look quite right, and I'm working, the ARINC 825 community has been very cordial and really working with me on this, so the answer isn't out yet. But what I found is when I read the specification that there were some typos and there's some things to look at. So if you're using this, you really want to take another look and make sure you're doing the right thing. The missing there's a missing +1 on this polynomial, or at least I would consider it. It is a polynomial. It does give you a CRC, but it turns out it only gives you 14 bits with its effectiveness rather than 16. And the initialization values that were put in had 3 Fs FFF and 3 Fs FFF, and they should have had 4 Fs, and the test string needed to have a missing 0. So that's going to be updated in a later version of the standard. And the point of this is that when you read about CRCs, you want to go in and you want to make sure that you check it for yourself. You just can't take stuff like this on blind faith. And I think I just talked about all this. So the working group and we just had a phone call a couple weeks ago, and we're working on this, and that'll be resolved, of course. By the way, I did see a question come up, and I think we're going to take care of all those things at the end, and I'll go back to slides as they are appropriate. For Ethernet, Gigabit Ethernet uses an 8-bit 10-bit encoding, and so that means every 8 bits of physical data are encoded as 10 bits. And that helps you maintain DC balance. It turns out it's not quite enough bit patterns to be completely DC balanced, so they shove a running disparity. Either I'm borrowing a bit or I'm adding a bit across to the next symbol. And there's some previous work, James in 2005, showed that strict running disparity bookkeeping is required to avoid compromised error detection. I did some simulation, and I didn't find a reason to dispute that. I didn't have the resources to really dig in to the point of doing something exhaustive. But there's a concern that if you have these clusters of bits, if you have an 8-bit symbol, now 8-bit 10-bit is a little more complicated, so I'm going to simplify it. But if you have a 10-bit symbol that represents 8 bits, the worry is if you flip 1 bit out of the 10, then all 8 bits change. And that will get past the Hamming distance of the Gigabit Ethernet polynomial, which is the IEEE 2.3 polynomial. And what they found was that if you strictly enforce running disparity and throw out illegal symbols, it doesn't seem like this is a problem. But what they also found was that some Gigabit Ethernet receivers are not strict. They're permissive, and they say, well, you know, if this is an illegal symbol, forget it, I'm just going to round it to a symbol I like. And in those cases, there were issues. So if you're using Gigabit Ethernet for aviation, you want to make sure that the receiver has strict enforcement of symbols or its potential vulnerability. I don't have definitive answers on that, but we ran into it in the course of the study, and I want to make sure people know to worry about that if they need to. Okay, switching to the next section, this is mapping to DO-178 criticality levels. This is the contract wording. It would be more correct to say the functional criticality levels. Thanks to Walt for pointing that out, but so you can think functional criticality go through here. So this is the Honeywell guys put this together. I think it's great stuff. And the question is, gee, is there an easy rule to just say, always use such and such a type of CRC and you don't have to worry about it? The bad news is no. The good news is there's a fairly straightforward methodology. You can go step by step and figure out what you want to do. So we're going to have an error coverage argument based on criticality of the functions using the data, how the errors affect those functions, and that doesn't have to do with CRCs. That has to do with your system. The probability of error occurrence given the size of the data protected, that's sort of the stuff we've been hearing about, and maybe other subordinate factors, and we just heard about a bunch of the kind of things you have to worry about beyond just CRC. In terms of the error coding, the dominant factors are Hamming distance of the code, the error exposure, and the consequence of detected error. So some background information. We're talking about error detection usage only in avionics, which is what we're investigating. We're looking at the existing data bus guidance, which is FAA Advisory Circular 156, paragraph 4, which doesn't, 20-156, paragraph 4, which doesn't say a whole lot. There's a flowchart of the process and an explanation of each flowchart step. We're using a fictitious example. So we're looking at error coding for data transfer systems. These are some avionics applications. It could be data transfer. It could be for memory. It could be for transferable media. And for each of these, you're going to have slightly different concerns. So this is a generic approach, but you have to take into account what your particular application is. We're only looking at random error coverage. So we're not looking at complex IC failures. In particular, we're not looking at hardware failures that introduce patterned errors. And the problem with patterned multi-bit errors, that might be the pattern the CRC doesn't know how to catch. We're assuming everything is random and any kind of vulnerability. And we're not worrying about symbol encoding, data compression, encryption, all the kind of things we talked about and more. So for data transfer system, the data integrity requirements are the data that passes between LRUs and so on must remain accurate. And you have to worry about the maximum error rate per byte expected for data transmission. And where applicable, the data bus provided means detect and cover. But it doesn't tell you what to do. It just says you have to do something to simplify it. And while specific to onboard data bus systems, it's applicable to anything, RF channels, Ethernet where you carry stuff around. You know, at some point, anytime you're moving data, you want to make sure the data on the far end is the same as the data you intend to send. And so we're using data transfer to mean one or more data networks within an aircraft or anything that gets data, maybe the USB plug into load data. It doesn't really matter. And we're limiting ourselves to CRCs and checksums. There are certainly more sophisticated data protection strategies you can use that are used on storage media, but we're just talking about CRCs and checksums. In order to do this, we have a little flowchart here. And so we're going to go through this step by step. You can see that there's letters by every box. We're going to go through them in turn. You have a requirements determination flowchart, and we're going to determine which functions, determine criticality, determine level of exposure, calculate, and then calculate required error coverage going down the left. And the right, we're going to determine the error model. We're going to determine which errors are dangerous, calculate the dangerous error probability. Now, for a lot of this stuff, we can't tell you what matters because it all depends on your system. What we're going to do is try and explain a flow that kind of makes sense and then leads you to something that you can concretely apply to picking a CRC or a checksum. So our example is, we're going to have a fictitious example. It's purposely picked not to look real. To paraphrase Hollywood, all the bits appearing in this example are fictitious. Any resemblance to real bits, living or dead, is purely coincidental, so please don't try and read your system to so the example is an autopilot control panel that uses a redundant data bus network to talk to a set of autopilot computers. This example increases the criticality of the function by ignoring the fact that pilots are supposed to know and maintain assigned altitudes. We're just assuming the system is the only thing. We're trying to make it simple so we can get through it as an example. And we're going to look at all the steps. So steps A and B, we're going to determine which aviation functions supported by the data transfer system and determine the criticality of these functions. And in this case, we did an assessment of the systems, and we find that what it's doing is it's incrementing or decrementing altitude hold changes. So instead of sending a new value, it's doing an increment or decrement. And you might immediately say, gee, that doesn't sound like a good idea. We know, but we picked it because it makes a good example. And the reason is that if you have an incorrect increment or decrement, you're going to permanently get stuck with an offset that's wrong, rather than a system which sends an absolute value to which the new one just overwrites the old one. And so that, because of that design, if for some reason you decide to design it that way, you need a higher level of error detection than if you didn't. And so that could lead to a mid-error collision, and that would be a 10-9 kind of thing. For step C, we determine each function's level of exposure to failures. And because this system uses increments or decrements, we have to basically not permit any undetected errors in the data bus message. You have to detect all the errors to the degree that get yourself down to 10 to the minus 9 per hour. We then calculate the maximum allowed failure probability, and we're going to say the PUD is 10 to the minus 9 per flight hour. That basically, as soon as there's an undetected message, then that's a potentially catastrophic failure for the aircraft. Step E, we're going to determine the error model and its undetected error probabilities. And we're going to say the autopilot is connected via data buses directly to the autopilot computers. And so we use the results of bit error testing, which we're going to talk about. That's trickier than it might sound later on, to determine error probabilities. We're assuming there's no complex devices. So if you have a network switch or something where it pulls the bits off, it strips the CRC, or even if it doesn't, and it massages the data and it sends it back out, this CRC or checksum isn't going to help you with those. So we're assuming it's just a wire and there's no complex devices that could introduce pattern corruption. And in this example, we say testing shows a bit error rate of 10 to the minus 8. So a measured bit error is 10 to the minus 8, so clearly we need to do better than that to meet the safety requirement of 10 to the minus 9. And that's 10 to the minus 8 per bit, and there's a whole lot of bits being sent, so you're going to see a whole lot of faulty messages being sent. So we're finding the bit error rate. This is sort of an aside, but we have to confirm it by testing. Just because the manufacturer says it's the bit error rate, or the standard says it, doesn't mean that's what you're going to see on your aircraft with your cables and connectors, which might just not be the same as the COT standard that was tested by the manufacturer. It's in an aircraft, which is probably a less benign environment than a desktop or office environment. The standards may be different for testing. The COTS component only need to work for the main customers, so car environment may not be the same as the aircraft, and the guys who make cans mostly care about cars. That's their big market. And they may not have to meet the bit error rate requirements for all scenarios. They may not test scenarios you care about. In particular, they're probably not up to aviation standards. For example, the car guys typically don't do lightning tests. You don't hit a car with lightning expected to keep working. That's just an example from my experience. So you can't rely on the COTS manufacturer component vendor test. Therefore, you're probably going to have to test your system for bit error rate, and you may have to actually monitor it during system life in case you get degradation. Now, that's all kind of aside, but what we're pointing out is you don't want to naively take a bit error ratio from an automotive application note and just plug it in. You're probably going to have to test the worst-case environment. You're probably going to have to test the worst-case bit pattern, which, depending on the network, will vary. You need the worst-case I pattern for the most degraded signal. And I'm skipping some of the details here, but you're going to have the notes to look at. And you're going to then compute the bit error rate, which is the number of bad bits output by the receiver under test divided by the total test. And you have to send enough bits. If you have a 10 to the minus 12 bit error rate, you're going to have to send a lot more than 10 to the 12 bits to get a comfortable number. You also have to worry that during aircraft life, the failures might increase the bit error rate as stuff wears out, as stuff gets old. Your bit error rate might go up, and you're going to either have to monitor it and say at some point the bit error rate is too high, so we're just going to declare this failed. And you can do that by detecting the number of bit errors you see. You can never know how many undetected bit errors you have, but you know how many bit errors you have. And when you see a lot of them coming in, you basically have to assume some of them are also undetected error. So if you see an elevated bit error rate of detected ones, then you have a spec for how many you're going to tolerate. When you exceed that, then you've got a problem, and you have to declare the maintenance or do some other corrective or mitigating action. But the important point is when you monitor bit error rate, it only tells you that the symptom. It doesn't tell you which bad messages are getting through. It's a little tricky. You have to think it through carefully. Okay, going back, assuming we actually have gone through all those hoops and actually have a realistic bit error rate that is actually representative of what we're going to see on the aircraft, you have to determine what errors can be dangerous. And I'm going to go down a path that actually doesn't get you where you want to go. It's sort of the intuitive path you might want to go down, but I'll show you why you don't want to go down it. You could say that there's an autopilot control panel in the autopilot computer. The messages are 64 bytes long, but only 4 bits matter. So you have a 4-bit altitude decrement, which is sort of takes 4 bits. And if those are corrupted, you could have potentially catastrophic failure. But if any of the other bits are not corrupted, it's okay. And note that 64 bytes is sort of the minimum Ethernet frame size. So you can calculate the dangerous error probabilities, and you can say, there's a bunch of math here. You can see a bunch of large number of digits precision, more than are justified, but we just sort of wrote them down. We didn't try and worry about how many digits there are. And what you have to worry about is that simplifying things. Let's see, here you have 4 altitude bits, and so you're saying, gee, what are the probability that any one of the 4 altitude bits is wrong? And it's kind of a moderately low probability. And then it sends messages at 20 hertz. There's so many messages per hour, and you compute it down to a probability of 2.8 times 10 to the minus 3 per hour, and that's certainly worse than 10 to the minus 9, so it's a problem. And so what we're doing is we're saying, what are the chances that any one of the bits that we care about is wrong? And so then you want to calculate the required error coverage. And the error coverage has to be such that the conditional probabilities of a particular number of bit patterns, which depends on the bit error rate, number of critical bits, and all that, times the probability of the error coding design is less than the maximum allowable failure rate for the message. In other words, you have to make sure that the number of these 3 times 10 to the minus 3 messages per hour, those are the number of faulty messages. How many of those get past the checksum or CRC? That's the undetected error fraction is what you care about. And so what you can do is you can say there's C. So it's the coverage, the simple coverage, the probability that one of them is undetected. And you can say, and so there's some math. You can see that you end up having a bunch of math that has to do with how many messages you're sending and what's the probability that one of these messages out of all of them is bad. And so basically now you have to say how many times, what are the chances you're going to get lucky and none of them are bad within an hour. And that times 72,000, because that's how many messages you can have an hour, has to be 10 to the minus 9. And that gives you several 9s. So you have to have 99.99997% coverage on each message. And this would be this would be sufficient only if the following were true. The hardware software that does the error detection never fails. Can't guarantee that, so you have to put that in. The error code protects only these 4 bits rather than the whole message, and that's a problem. The error code itself never suffers any errors, because we didn't put in a probability that the error code has bit flips, which you have to do. So any of these problems, the data word could be corrupted, or the check sequence could be corrupted. And so the issue is, while this might be a kind of approach you might want to use, it's really hard to guarantee that the error detection code isn't corrupted, or that the error detection code is only handling those 4 bits and none of the rest of the system. In practice, that isn't what happens. So in practice, what you do is you apply it to the whole data word ring it. So in this example scenario, we assume the error detection mechanism's failure rate is 10 to the minus 7 per hour. So we can assume just some sort of failure rate of 10 to the minus 7 per hour. We're going to assume there's scrubbing before each flight. And so this is tricky because on Ethernet, you have to actually make sure that the CRC mechanism on Ethernet is working. And it's hard to do that unless you have a test ability or you have the ability to inject potentially bad messages, or else you don't know whether the CRC check works before each flight. So that's the kind of issue to think about if you use commercial components. And that's why a lot of people put a CRC inside the message, because that's something they can scrub, they can test themselves. So the combined error probability of an error mechanism failing and error occurring is about, occurring the 4 bits per hour is about, is about 8.6 10 to the minus 10, so that's better than 10 to the minus 9. Without scrubbing, it's going to be higher because you're going to have to be over the life of the aircraft, and it may break. You won't know. So if you're going to do scrubbing, that's going to help. You can do black box or white box scrubbing, and that has to do with figuring out the error patterns or testing the components. But the idea is that you're going to have some way of knowing whether or not the CRCs are actually working. Now the catch is, that would be nice if we were only worried about the 4 altitude bits, but it's pretty common for data to be sent that some of the data is critical, some of it's not. And in this case, we only care about 4 bits, but we have a lot of other bits that actually can affect things. So if you have an error detection code that covers the whole 64-byte message, which is what people usually do, you can't just say, I have an error detection code of Hammond distance 5, and that guarantees all 4 altitude bits are protected. And the reason you can't say that is if any of the other bits get corrupted, then that takes away from the Hamming distance 5, and you could have one of the 4 altitude bits corrupted, but 6 or 7 or 8 other bits in the message corrupted, and that could get past your CRC at Hamming distance 5. So that's the catch. You have to look at all the potential faults across all the bits, including the CRC itself. So even if you have a 4-bit altitude, 4 altitude bits, you have to look at the bits that could flips that could also happen to the CRC protecting. In this case, CRC is across the whole message. And so what people really do is they just say we're going to treat the whole message as critical. So treating the 4 bits as critical is sort of a best case that you never really see. What you really do is you just say, let's treat the whole message as critical, and it's protected by some sort of CRC. You have 72,000 messages per hour times 64 bytes per hour, and do some math, you come up with the errors per message. So it's 5.2 10 to the minus 6 errors per message, and that's about 0.3 errors per hour. Wow, that's a lot of errors. So 3 times an hour you get an error. You want to get down to 10 minus 9 of undetected errors. So you're going to need a pretty good error detection code. As an example, if you have a 16-bit random error detection, so this is a Hamming distance 1 mixing function that's just basically a pseudo-random number generator, and it's hard to get unlucky and have that pseudo-random number come out the same with a 1-bit error, but it could happen. And so if you just have a 16-bit random number appended, that gives you 5 times 10 to the minus 6. That's not good enough. If you have a perfect 32-bit random number error detection with Hamming distance 1, that gets you 8.7 10 to the minus 11. So that's likely. So this is worse than any real checksum. All the real checksums have Hamming distance 2. But in Hamming distance 1, it's actually good enough. So pretty much any 32-bit checksum is going to work in this case. You can do better, but that'll get you there. And so an answer you may get with all this is that really anything is good enough, and that's okay. It depends on your system. But now what we had to do in this is we had to use a 32-bit checksum. A 16-bit checksum wasn't good enough. So let's see if we can take some credit for using something better than a very simplistic random number generator. If we're going to use an actual CRC, for example, a Hamming distance 4 CRC is going to do the job. So the Hamming distance 4, so if we select BAAD, which is one of the polynomials, and see the polynomial expression here, Hamming distance 4 coverage, 512 plus 16 bits of code words. So now before it was 64 bytes, but it's 512 bits plus 16 bits. The undetected error probability is 64,510. Remember I said Hamming weight? The Hamming weight of this is 64,510 out of all possible 4-bit combinations of 528 bits of code word. That's how many are undetected. And so we look down at the analysis and we see all 1, 2, and 3-bit errors are always caught, so we don't worry about those. So this is 16-bit CRC. It's going to give us Hamming distance 4. All 1, 2, and 3-bit errors are going to be caught. All 4-bit errors, which is all combinations times the 4 bits error times the rest of the bits of non-error, so that's probability math. We're going to have the probability of a 4-bit error even occurring is 3.2 10 to the minus 23. So what we could really stop there. What we're saying is if you have Hamming distance 4, it's so unlikely you're ever going to get a 4-bit error in the first place if you believe that random independent bit errors at a bit error rate is the right fault model. So you don't have to worry. Any CRC or checksum will do it Hamming distance 4. So if you had no Hamming distance 4 coverage at all, then you're going to have 2.3 10 times the minus 10 minus 18 undetected errors per hour for any Hamming distance 4 code. And you can actually do twice as good with that with a good CRC. For 5-bit errors, the contribution is too small to matter. There's just so unlikely to happen. You're going to get 10 to the minus 24 5-bit errors per hour in the first place, and that's before you detect them. So the moral of the story is that if you can get yourself out to a good Hamming distance, you get to the point where you're just never going to see that many bit errors, and you're done. But that's why we say later it's all about the Hamming distance. So to put this up at a higher level, I know that was kind of detailed, and I sort of blew through the math, but it's on the slides afterwards. A simplified approach to coverage is you compute the number of expected message errors per hour, and you say how many 1-bit errors am I going to get, how many 2-bit errors, how many 3-bit errors, and so on. And the hours per hour is a function of the bit error rate, the message per hour, and the total message length. And you figure out, all right, how many can I tolerate? At some point you're going to say I have a number It might be 10 minus 9. It might be, if you can take credit for system level fault mitigation, it might actually be more frequent than that. And at some point, the messages with that many bit errors are just never going to happen. And you find out what that Hamming distance is. So if they say 4 bit errors are never going to happen, that's fine. I can have a Hamming distance of 4. If you need 5 bit errors, that's fine. You could say 5 bit errors here are less likely than 10 minus 9. That means, the Hamming distance is 5 is okay because you're just never going to see it. So you pick a code that has Hamming distance to whatever your tolerable threshold is, and you're done. Now, if you're in a border, if it turns out that, well, 5 almost gets me there, but not quite, then you have to need detailed checksum information that is going to basically give you the undetected error fraction, and only then is it worth taking credit for the undetected error fraction. Because the undetected error fraction is usually something like 1 over 2 to the k for a CRC. It's a few orders of magnitude, but the bit error rate usually drives the problem. Now the question, do you use a checksum or CRC? Given this, it's actually pretty easy. If you only need Hamming distance of 2, a checksum is probably going to work for you. Hamming distance of 3 for some checksums at small length. But as soon as you have so many bit errors expected during the life of your system that you need Hamming distance 4, CRC is your only choice. And a CRC will, of course, always provide better coverage in terms of undetected error probability for a given Hamming. Okay, so wrap up in discussion, and it looks like we'll have plenty of time for questions, which is good. We came up with a CRC checksum, 7 deadly sins. We're taking some liberties with this, but it's a catchy way to come up with some bad ideas of things we've seen in CRC in industry and the literature. The first sin is popularity. So picking a CRC based on a popularity contest instead of analysis. This includes standard polynomials. So you should never say, well, we use this CRC because my buddy Joe used it, or because it was in this paper, or even if it's in a standard. Because it may be fine or not for that standard, but it may not be the right one for you because your usage will be different in some way. And you should always look at data on the CRC performance instead of just picking it because someone else used it or it was already there. Number 2 is to pick a good checksum that's as good as a bad CRC. There's some publications out there that say a checksum is just as good as a CRC. I've seen this data, and what they did was they picked a really bad CRC. They didn't know it. They didn't do it on purpose. They didn't understand it mattered. They pick a bad CRC, and they say it has the same distance as a Hamming distance checksum, so it's okay. And that's just not what you want to do. CRCs are essentially always better than checksums. It's just a question of how much. Checksum may be good enough. It may not, but you want to go through that decision process to decide if it's what you're after. Another one is a lot of the evaluation papers will say checksums and CRCs are just as good each other because they use a randomly corrupted data. What they do is they feed totally random data through and decide whether or not it gets detected. Well, any checksum there is pretty much looks the same on totally random data. But that's probably not what you're worried about. You're probably worried more about small numbers of bit errors. So any checksum works on totally random corruption because it's just a numbers game. They match or they don't. The less corruption you have, the more of a difference there is between CRCs, checksums, and other functions. So almost always what you want to look at is the performance on small number of bit errors. In other words, pick for good Hamming distance and don't let the randomly corrupted data results distract you. Another one is people blindly choose polynomial factorization to CRC, and they say, oh, I want divisible by x plus 1. Sometimes it's good, sometimes it actually hurts. They say, all right, I'm picking a factorization because this will give me certain properties, and with a couple very limited exceptions at long data word lengths, particularly primitive polynomials times x plus 1 sometimes help. But other than that, the factorization doesn't mean a lot. There are really good polynomials and really bad polynomials with the same factorization. The only way we found to know what the answer is, you have to actually do the brute force analysis and know what the answer is, and that's what we've been trying to publish. Some people fail to protect the message length field. You might remember that if you corrupt the message length field, you look in the wrong place for the CRC, and it basically gives you a Hamming distance of 1, regardless of what you tried to do. Number 6, they fail to pick an accurate fault model. And they say, basically, we added a checksum, so we've got our body armor on, and we don't have to worry about anything because we have a checksum. Well, that's not true. Certainly adding a checksum is a good thing, but you have to grind the numbers, you have to grind the math. In particular, you have to look at how often the bit errors will happen, and how often multiple bit errors will happen, and how often it'll happen to the point it gets past your Hamming. that's what you have to look at to really know what the safety argument is going to be. And the last one is they ignore interaction with bit encoding. The bit stuffing on CAN is kind of a classic. It hasn't been advertised that much. It's been known for a while, but it's hard to find the literature on it, so we're trying to raise awareness. And the 8B10B on gigabit Ethernet seems to be okay, but you have to be careful with things like that. You have to make sure. There are possible things so wrapping up, there's possible things we haven't done. One is we haven't looked at other fault models such as bit slip, bit synchronization. That can be a problem depending on how you design your system. There's data byte ordering errors. There's all sorts of things that once you get interstages in, we didn't really address that because those sort of go beyond the classical CRC and Checksum stuff. We only understand some of the cross-lane interactions, but what you should have gotten out of some of those stories was that how you encode your bits actually affects whether the CRC works or not, how you frame your messages, whether or not you detect poorly encoded bits. If you have Manchester encoding, you detect bit form violations. That actually happens a lot. We saw that in train control network. If you have stuffed bits from everything I can see are kind of evil. They're going to cause problems. So you can take credit for some. You have to watch out for some. And we don't have a definitive study on it. We just have some observations made. We haven't looked into alternate hybrid approaches. Is there a pair of CRCs that gives a higher Hamming distance to the pair than any one in particular? We don't know of one. One could be there. That's just a lot of grinding away on the work, and it's a hard thing. In particular, if you're designing safety layers and you want to have multiple CRCs nested, that's an important question, but no one really knows the answer other than all the ones I've seen didn't really work as people hoped they would. Another one is cryptographic secure hash functions. In theory, they only give you Hamming distance 1 because there's no guarantees on the bit patterns. If there were guarantees on the bit patterns, it wouldn't be a good cryptographically secure function because it'd be structure you could exploit. And so encrypting something only gives you Hamming distance 1. Now the good news is that if you have a 256-bit hash function, that's a 1 in 2 to the 256 chance of getting unlucky, but it's still only Hamming distance 1. So you have to watch out for that. Bit for bit, you want to use a CRC instead of a cryptographically secure hash if you have limited bits. We have not yet done an analytically exact evaluation of other codes. We haven't looked at 64-bit CRCs. They're out there. They're not that heavily used. It takes a lot of compute power to do those. The ATN32 effectiveness, we put a worst-case bound on, but actually we should put a best-case bound on. It might even be worse because we didn't do exhaustive testing. But clearly, if you have long data words, that checksum is going to be less effective than a Fletcher checksum. And we haven't looked at high-level system effects like the interaction of compression and encryption. Although I'll give you a hint, you always want CRC outside the encrypted data because if you get a bit error on encrypted data, when you decrypt it, that bit error is going to propagate all over the place. You're not going to get a good Hamming distance. And we have, from what we've seen, we think a lot of times the safety layers involving CRCs probably aren't as good as people give them credit for. We don't have specifics, and that's something that might be worth a closer look. The next step is a final report has been submitted to the FAA, and they're taking a look at it, and it will be published in some form in due course. That's up to the FAA folks. Again, you can get a copy of these slides at that URL, and I'm going to leave this up at least for a little bit while we do questions. And if you have follow-up comments, Barbara Lindbergh at FAA is going to send out that email she talked about to all the participants afterwards, but that's her email address if you want to contact her. And if you go to the website, there's some backup slides. I'm just going to flip through. It shows how the subtasks were and a little bit more information, but I'm not going to talk to them. Instead, I'm going to switch over to questions.
Okay. Do you have the Q&A panel up?
I have it up.
You just want to read?
I had to shove it off to one side so I could see my slides, but I have it up. How do you want to go through this, Walt? Or Mike, excuse me, Mike.
Oh, that's okay. Just go ahead and go through the questions like you would like to and just answer them. What I can do is I can unmute the individual, which is probably the smart thing to do. Because I think there's a lot of these are going to require interaction. That's going to be a lot easier than just retyping in the chat window. So your first question, do you want to deal with the first one from Edgar?
Yeah, well, let me just read that one. I don't want to go interactive with it, but the comment was the CAN message with the stuffed bits appeared to have an error in it. I don't really want to go down into finding the typos in my slides. I'll put it up for a second, but I'll tell you the one thing is that when you have a stuff bit, this is CAN is a 5 in a row rule, that if there are 5 bits in the row that are the same, you get a stuff bit. When you have a stuff bit, it counts as one of the 5, and so that's one of the tricky things about it. And if given that, Mr. Van Trotha still thinks there's an error, I love email from him, and we'll sort it out. The point of that slide isn't the exact picture. The point is more stuff bits cause cascaded bit errors that get past CRC, and I want to leave that one there.
Okay. Let me know whenever you want me to unmute somebody.
Okay. The next one, let's unmute James Muir, and as I read that one, we'll talk about that one. So I guess I don't know if anyone, Mike, can everyone else see the questions, or is it just me?
They should be, but just go ahead and reread them.
I'll read it, okay. So I have, please relate the error rates to the DO-178 levels as it is concerned as the error rate approaches the desired level, or is, for instance, only 2 to 3 orders better than the needed level. Is not only the gross number of undetected errors, but unit time, in addition with stuff, okay, let's go back to stuff bits. So let me take a shot, and I think Kevin Lamont, he might want to go after that one. I know I went through the math kind of fast because I didn't want to get everyone completely bored about it. What we're doing is we're definitely taking into account. You have to let me just explain the high level and see if that addresses the question. When you look at this, you have to look at the probability of bit errors, and then you say the bit error rate affects how likely it is you're going to get a message with 2 bits or 3 bits. And you say, fine, I have Hamming distance 4, and so at Hamming distance 4, I'm only going to see a 4-bit error every so often. And that's a per hour number. And so you then have to decide how many 4-bit errors per hour can I tolerate given architectural level mitigation. Maybe there's 2 channels and a cross compare and all that stuff that we don't take into account. So you definitely have to get it in a higher system context. And that system context might give you several orders of magnitude improvement. The way we look at it is you first look at the system context and boil it down to a CRC undetected error budget. You say, my CRC has to have a certain performance given everything else, and then you pick in a code that provides that performance by picking the right Hamming. So, Mr. Beer, did that answer your question, or do you want to follow up?
I guess the beauty of your presentation is that by the ability to achieve higher Hamming distances, you can, and you very articulately described how that improves things more than anything else. In CAN, I feel that we may be burdened by not being able to do that, and so I buy your argument on the Hamming distance too. That's well proven here, well demonstrated. And then the question arises: what are the mitigation abilities of a Hamming distance 2 against word length, similar to the charts you showed with different Hamming distances, and with a Hamming distance limited to 2, and the words and CAN obviously being much shorter, maybe the issue is not so great until you try and achieve something higher than 10 to the minus 7 or 10 to the minus 9, or try to reach 10 to the minus 9. And the second part of the question is that just by reaching those levels doesn't completely relieve the concern, as it's not until you're 2 or 3 orders of magnitude above your desired level that you can then be able to dismiss any real impact. And I'll stop.
Okay, so let me do it in reverse order. If you're at 2 or 3 orders of magnitude above your desired level, then basically I would say that's your goal. Just set that as your goal instead. So if you don't feel comfortable until you're at 10 to the minus 11, then just say, all right, I have to be at 10 to the minus 11. Now what CRC do I need? So see that as a system level issue rather than a CRC issue, because ultimately you set a budget to CRC, and the number is what the number is. So that's how I would sort of address that.
Right.
Now the bad news is with Hamming too, it's hard to get that right. This is an ARINC 825 thing specifically, as I know, and
yes.
and I'm sure that's what you're referring to. the best I know how to do with current technology is if you have that high-integrity CRC inside the CAN message, let's say it takes 2 bytes out of an 8-byte payload plus the header, that does give you an improvement in undetected error fraction. So on a good day, generally, pretty much any CRC, it doesn't really matter which one, is going to give you 2 to the K improvement. So if you have a 16-bit CRC, it's going to reduce the undetected error fraction by a factor of 65,536. Okay? And so the more bits of CRC you put in the payload, the more attenuation you get. The bad news is it's not handling this undetected error fraction, so it's expensive, right? And so the question is, how many bits you forward in the payload, and does that give you enough of, it's 2 to the K, where K is the number of bits. That's the attenuation you get. And so putting the CRC inside the payload definitely works, but it's only a 2 to the 16 factor, not a Hamming distance factor, and that's why it's problematic.
I don't want to take the time here, but that's the statement we've arrived at before, and we'll want to explore a little bit more in depth later on.
Yeah, we can explore more. And actually, you get another factor of 30 because it's hard to get the bit stuff error to propagate. That's why I sort of showed that slide.
Okay. Again, this gets pretty deep in the weeds for this call.
We can follow up later, but this way everyone sort of heard how it turns out, which is great.
Good.
Okay, and I think I got both parts.
Yes.
So Mike, I think the next one is Mr. Sorry about this, Van Doinhoff, Mr. Van Doinhoff. And the question is, have you done any work related to network security? I have done some. In particular, have evaluated how hard it is to forge spoof a message with specific intentional corruption and correct checksum or CRC. For example, does a dual checksum CRC prevent spoofing? Okay, two-part answer. The first answer is if I want to fake a CRC, I can do it, and it's just trivially easy. If you know math, it's trivially easy. The second one, even if you don't know the math, if you have a 16-bit CRC, there's only 2 to the 16th polynomials to try. So you just try them all until you see which one works. So even a mathematically unsophisticated attacker can pretty readily use brute force. It's a 232-bit CRC. Fine, there's 4 billion to try. There's only 2 billion to try. Try them all. It's not going to take that long. So a CRC absolutely does not give cryptographic security. Pairs of CRCs just are not secure. That's pretty much a hard and fast rule. Have evaluated how hard it is to spoof, so it's pretty easy, and this is one of the reasons I recently graduated a PhD student who figured out how to add cryptographically secure integrity and authentication checks to CAN, and he did it by amortizing the cost of secure hash functions across messages. And that's probably as far as I want to go in this phone call, but you're welcome to send me an email, and I guess you're unmuted for follow-up, but if you send me an email, I'll be happy to send you a pointer to the paper if you have any trouble finding. Any follow-up?
No, I'll send you an email.
Okay, happy to do that. The next question is Stephen Friedrich, so if you can unmute him while I read the question. This analysis is just on data payloads of specific length. What is the guidance for checking stored program data? And so I tried to address it. I know I didn't spend a lot of time on it. Basically, the stored program data is the data payload. And so however big a chunk of stored data you're protecting equals the data word length. And you notice that as CRCs protect a lot of data, the Hamming distance degrades very significantly. And so if I had to protect stored data at a particular number of bit flip budget, what I would do is I could compute a CRC for each chunk of data. I'd look at that table I showed. Let's see if I can go back to it. What I would do if I were protecting data is I would go back to this table here, and if I wanted a 32-bit CRC, I would say, all right, how many bits, notice that these are bits, how many bits am I trying to protect? And I would chunk it up and say, fine, I'm going to chunk it up into 11K bit chunks, and then I can use this CRC. This is the standard CRC 32 from 802.3. in size chunks, but maybe what I really want to do if I want Hamming distance 4, I use this CRC, and now I can have basically two 56 megabit chunks that are each protected by its own CRC, and then you just iterate. So you're going to have to break your data down into block sizes small enough that you can get a CRC to give you the Hamming that you want. Any follow-up? Did that answer the question?
He's going to have to enter in the chat box in that we don't have a phone line with him.
Okay. I see another question from him below, though. Okay. Well, we'll give him a minute, and I'll just keep going down the questions, and if anyone wants to follow up, we'll go down. Mr. Van Trotha said agreed, no problem, so that's good. I'm glad that answered it. We have another question from Mr. Friedrich saying, how does one, he said he answered the question. Great, thanks. The next question from him is, how does one test the bit error rate in an efficient and effective way? Kevin, are you on the line?
Yes.
This one's all yours.
The classical way of doing a bit error rate test is there's hardware to do that where you generate typically an LFSR at the transmit end and you check it at the receive end. But it has to be done on the hardware you're actually really going to use in flight. You can't, say, do it over an office Ethernet and say, okay, that's the same as it's going to be in flight. It's got to be the same wire, same cable harness, same connectors, same receivers. Now, a difficult piece of this is that the receiver for the bit error rate test is usually integral with the bit error rate tester, has to have the same threshold characteristics of your real receiver chip. So you got to match those, and that's difficult to do. One thing not to do is you can get logic analyzers and oscilloscopes that will look at eye diagrams, and they'll tell you, here's what the bit error rate is for that eye diagram. Well, only if the receiver that you're going to actually use in your equipment is the same receiver as is in that test equipment.
Okay. Okay, sounds like there's an okay. Kevin, did you want to say something about data scramblers while you have the floor?
Yes, several times during this presentation we talked about 8B, 10B encoding for gigabit Ethernet. There are other encodings, like for 100 megabit for Ethernet, it's 4B, 5B, and a number of these also use scramblers. So the 100 megabit Ethernet uses a scrambler that I think is 7 bits long. And so now when you start looking at the single bit errors propagating, they can propagate through the symbol, so you can get a 1-bit error that will convert a 4B, 5B symbol into having up to a burst of 5 bits. Then that enters the scrambler, and that can add another 7 bits. So you can get a span of 12-bit errors on a single bit hit on 100 megabit Ethernet. So you have to look at everything between when you calculated the CRC and when you checked it. Anything that can cause a propagation of errors has to be considered.
That's a great point, Kevin. So just to make sure everyone got the big picture, you can have a 1-bit physical flip on the media or in memory or wherever it is, and that can manifest as many, many, many data bits flipping by the time it gets to the CRC because of this aggregation and scrambling effect. And so that's why it's so tricky. And that was the bit stuff, and it's the encoding and the scramblers, all those kind of things. Sort of the physical layer can undermine the CRC in ways people often don't think about. So that's an important thing to keep in mind. Okay, and it looks like we got an okay on that one. Next one is Paul Miner. Hi, Paul. It's been a while. Good to hear from you. This study seems to address randomly distributed single-bit errors. How do the results change when mapping to encoding blocks of memory where a single fault might corrupt a byte or a word at a time? And the answer is we haven't looked at that beyond just saying that the good news is if you pick the right CRC, if you get 4 or 5 bits scrambled in a close together, the CRC is going to be more effective at detecting those than 4 or 5 bits that are all over the place. But we did not in particular look at, this is a future research area, and it actually applies to the things Kevin was talking about just as much to memory. And that is if you have bursty type errors that are scattered around things. So you have a burst error of 4 or 5 or 6 bits over here, and a burst error of another 12 bits over there. how good are the CRCs at detecting distributed burst errors is not something that I know that anyone's really looked at, and that's what you would have to do to answer that question. Any follow-up to that?
Yeah, I was just thinking that another mechanism where you might trigger bursty errors, and I think this was hinted at in Kevin's things with some of the phi layer questions, is at the SERDES itself, you've got possibility of transient effects triggering very tight bursts of errors that could span at least the size of 1 byte of information in an 8B, 10B, for example.
Yeah, that's great. So one of the things we did was we decided we're going to do independent bit errors, and small bursty errors is another fault model we haven't looked at. And if that's the kind of fault model that concerns you, then there's more work to be done on this. I absolutely agree with that.
Yeah. We were saying, Phil, that we left the active failure modes out of our analysis too, because correlated errors will challenge us.
Well, we hypothesized a big cause of correlated errors would be active interstages, but you could get noise events that also, it doesn't flip 1 bit. It's a noise event long enough to always reliably scramble 10 or 20 or 30 bits. And CRCs, if you only have a single burst, a CRC will detect any single burst up to the size of the CRC. So that's the good news. And so if you want to do 40-bit burst errors, you just pick a 40-bit CRC and you're 100% covered. The catch is if you have multiple bursts in the same data word, all bets are off. That's the problem.
A couple related issues. One of them is intersymbol interference. On high-speed data buses, wandering DC balance and reflections can cause data-dependent errors. And similarly with crosstalk, if you've got multiple buses in the same bundle, and those will also cause correlated failures that kind of invalidate our simple model of independent bit failures.
On the other hand, in defense of the model, if you do better at a bit error rate model, probably it's also better for all the other stuff. CRCs turn out to be better, and they're also better at burst errors. They're also better at a lot of other things. But the bad news is there's no current way to quantify how good they are at those kind of models. So if that's what your environment is, there's really no research that's going to tell you what the answer is. You can, if all else fails, you set up a Monte Carlo simulation, you get yourself some quad-core machines off woot.com like I did, and you let them crunch for a few months, and at least you'll have a better feeling for how it's going to be. But you're going to have to simulate it. There's really no way to know what the answer is going to be without some sort of evaluation. Okay, any other questions? Nothing else is coming up? Any other questions?
Okay, we do have one that showed up on the chat window here from Howard Lowe at GE. He was wondering how the FAA is going to make use of this material, and I'm going to turn that over to Barbara.
Okay, thanks, Mike. We have discussed internally already, I'm going to say this generically. We have discussed already developing some type of guidance material, and by guidance I do not necessarily mean an advisory circular. There are other approaches available to us to address this, so it is in the works and for FY14, but that's all I can say at this particular point in time. We've just, as you know, we've just entered this fiscal year with a short gap in our time frame, so hopefully we'll have something later in the fiscal year that we can provide, at least at a draft level.
I'd like to just add one more thing to that. This stuff is you really don't need, we intend to kind of wrap this into something, but you really don't need guidance to do this. This is to meet current regulations and probability numbers and stuff like that. You can include this in your safety analysis. This is the first bit of data I've ever seen that isn't hand-waving and how to actually meet your target goal. So, you don't have to wait for guidance from the FAA. This is stuff you can plug in. This is groundbreaking new content. So don't feel you have to wait for the FAA to use this. You can use it already.
And one more thing,
Mike,
Barbara,
okay.
this kind of echoes what Phil said earlier. The draft of the final report is already on the Software and AEH website under Research Reports. So it is a draft. Eventually, the final report, once it comes out editing and it has final publishing approval, that will be posted too. But right now, the draft final report is already there.
Okay, I've unmuted Howard to see if that addresses his answer.
Yeah, hi Mike. Yeah, thanks for that. I mean, we'll be interested in seeing what the guidance is, but I suppose one concern that leapt out from this is that supposedly internationally accepted standards for protocols are being called into question. And so I suppose we're sitting here thinking, you know, is the direction going to be, well, you've actually got to go off and test and prove that the protocols actually meet the defined standard for your particular application, and that sounds like a lot of extra work.
Well, you know, one of the problems we've always had is that people had you know, whenever they had an data integrity claim that they had to make, in many cases they would just reach for a standard that was unproven. There was a lot of, and I have a file that's almost 3 inches thick of material I've kept over the years, and I accepted it as, you know, lo and behold, it's been blessed, it's good, and I didn't realize what the problems were. I mean, I think the data that he has here gives you the stuff you need to use. You just have to be careful of what your error sources are and make sure you properly characterize those before you apply this.
So looking ahead well beyond 2014 probably, does this mean that, you know, as part of perhaps a soy audit, you know, the FAA would be looking for substantiation of why a chosen polynomial or CLC or anything like that reflects that particular system to which we're applying it to? Because I don't think you go that far at the moment.
It depends, and I apologize because I'm not going to say the FAA is inconsistent or any regulatory authority is inconsistent, but we have been inconsistent. And when I've been involved, I have asked for justification as to why you believe that CRC was good enough. My problem was I didn't, until this research, I really didn't understand how deep I should have asked. And so yeah, I think that should be something that goes on right now. It's not something that this is all of a sudden exposed as a problem. We should have been asking that for all along, and some of the ACO engineers have been. So the answer is yes.
Yeah. Oh, well, thanks for that. I mean, we've learned a lot from this, so we'll watch for the guidance and see how it evolves.
Okay. I don't see any other questions. Let's see. Okay, we do have another from Jim Mayer. He says the report is one thing, and under FAA auspices, it would be nice to have a statement from the FAA that endorses the report, or even if the FAA does not do anything further. The fact that we've released it indicates that the FAA has, and Barbara, if I'm saying this wrong, straighten me out, indicates that the FAA has accepted the content of the report. But when we write up whatever it is we intend to do, because we do want to recognize this a little further in some form, whether it be a handbook, whether it be a job aid, or whether it be some other type of thing, it's most certainly not going to go in as an AC. We just think that for the very reasons that Howard Lowe has brought up, that we're going to have to explain how to use this a little bit better even to our own people.
Well, I agree. This is Barbara. Okay, we have accepted, well, what we've put out on the web is a draft final report. So we have received that from the investigators. And as I said, there will be a final report that will be the final thing where everything is corrected in there. And there may be some give and take back and forth between the FAA and the investigators through the publishing cycle or through the editing cycle before it leads to publishing. So in all of our research reports, we put caveats to say that the contents of any research report are reflective of the investigators, the parties who actually do the research, and do not denote anything on FAA's part with respect to confirming or denying or considering it to be guidance or policy. So I'm hesitant to say anything more in that regard. Anything that acknowledges our recognition of something to be an acceptable means of compliance will come in the form of some type of guidance material. So that's forthcoming. As I indicated, we're talking about doing something in that regard. I don't know the vehicle that we're going to use. If you look at the draft report and just looking at what Phil and listening to what Phil provided today, this is an extensive amount of information, and some of it's very detailed and mathematically oriented, and typically our guidance material is not written to this level. So we're going to have to take and decide how best to or in what format to put that material. So we have some work to do and some discussion within ourselves, among FAAers in order to get it out. But the draft report is there for your reading pleasure, and I appreciate people being online and having that interest in seeing where we're going in that regard. So stay tuned.
I just put the URL for the draft report on the blog, right in an entry right above the slides, so everyone should be able to find it.
Okay, and also Barbara will include that link when she sends out the email to everybody when we have this available. Okay, I don't see any other questions, and we're right at the end, so I think we should probably close this up, and if there are further questions, address them to Barbara Lingberg. Wow, this has been a great presentation. I've received a number of private comments stating how valuable this would have been at the beginning of Project X. So, again, thanks to Phil Koopman for this highly informative and very useful presentation, and his team from Honeywell, Kevin Driscoll and Brendan Hall, for the research and the soon-to-be available report. I'd like to also thank all the attendees for showing up and your patience during the crazy government shutdown. And also thanks to Georgia Koutsaris for handling the very fluid, ever-changing, and quirky registration process that is WebEx. And, of course, Chuck Kilgore and his team at the FAA Tech Center for managing the research. And, as always, thanks to Barbara, who just makes things happen. We would appreciate feedback on how we could improve any future web-based presentations. Please feel free to be as brutal as you would like. Don't pull any punches. On the other hand, if there's something you really, really like that worked especially well, let us know, only so that we don't eliminate it from future conferences. And again, send all comments to barbara.lingberg@faa.gov as well. Anyhow, that concludes the webinar. Thank you very, very much.